Okay, so let's go ahead and finish up this last one. The balanced chemical equation we were talking about, N2 plus H2 yielding NH3. Now I put these two here. So I was just talking about diatomic molecules, and the reason that they are diatomic is because when they're by themselves, like nitrogen, it has 5 valence electrons. Okay, and so when there's another one in the same spot, it's going to want to be happy, so it will covalently bond 3 times, so you get something that looks like this. Now, nitrogen also loves one lone pair, so this is a perfect compound for him. Similar, like hydrogen has 1 valence electron, and so there's 2 here, so they'll share, and so you get H2 or N2. So you really have to watch for those. And now we go ahead and balance it. So we have our reactants on this side. Okay, they are reacting together to make our product. Okay, in some instances there's more than one product. And this arrow is the indication of the chemical reaction. Sometimes you can have the arrow with heat, right, showing that there was heat, or maybe it says stirring, or it has a different catalyst. And we can balance this. And you don't want to try to make your formulas balanced before you write them. Like, obviously I could write nitrogen plus H3 yields NH3, but this is incorrect. This doesn't make any sense, especially when we're following the rules and using diatomic molecules, okay? So we can see that that's really wrong. And you want to write all your formulas correct first and then balance it. So you see 1 nitrogen over here, 2 over here, so I put a 2 in front. That makes 6 hydrogen total, so to make this 6, I'd put a 3 out in front. So I have a balanced chemical equation. And then we would classify this as a synthesis or a combination reaction. Synthesis is like A plus B yields AB. Okay, we also have decomp. Decomposition reaction is when they decompose. So you have AB as a compound and it splits into A plus B. You have a single replacement, so you have AB plus C, and C replaces B. So you have AC plus B. You have double replacement, which you have AB plus CD, and it makes AD plus CB. Notice I put the C first because it's a cation is always the first one. You want to leave it the first. And then you have your combustion, just like a combustion engine. And so you're going to have some kind of carbon compound. And that carbon compound is added with oxygen, O2, diatomic molecule, and it makes CO2, or sometimes CO, plus H2O. Okay? So those are your 5 types of reactions. So let's go back to this one, the synthesis reaction here to make ammonia. If we have this equation here, we can make 3 different mole ratios from this. Okay, so if we come over here, we would have, let me just write that along the top again so I don't remember. So we have N2 plus 3H2 yields 2NH3. Okay, so we could write 1 mole of N2 is the same as 3 moles of hydrogen, H2. You could do 1 mole of N2 is equal to 2 moles of NH3. Little did you know back when you were balancing chemical equations that these were actually the amount of moles. Okay, we didn't know what moles were, so it didn't make any sense back then. And then we have 3 moles of H2 over the 2 moles of NH3. Okay, and this is basically what stoichiometry is the use of mole ratios. Okay, so I know some of you didn't get all the way through mole ratios, and maybe some of you didn't understand it, but on top of what we did with the mole, 1 mole is equal to the 22.4 liters, okay, or 1 mole is equal to the molar mass. Okay, these were our conversion factors that we could calculate here from the periodic table. Or that 1 mole is equal to the 6.02 times 10 to the 23rd. Okay, all of these were conversion factors, and basically in stoichiometry we're just adding these to that. Okay, And we used that handout that was the mole, and then it had liters up on top, and then we had representative particles, and we had grams, and we could use this idea, and that mole was the central thing. Okay, but here we could only go from one thing, so you'd have liters of oxygen to grams of oxygen, or grams of oxygen to moles of oxygen, or whatever, and we could just stay on that one. But now that we have this balanced chemical equation that we can make mole ratios, now we can start doing calculations using mole ratios and using what we knew prior, and we can calculate all sorts of things. Okay, and we can go from this compound to this compound. Okay, and so let's do an example of that. Let's say we have 15 liters of N2 gas, and we want to know how many liters of H2 gas we'll need to produce ammonia. Okay, and I drew this on the board in the classroom, and let me explain it a little better today. So now with the mole ratio, we can add to this that mole ratio here in the middle that takes us over to the other mole. Okay, and this could be compound 1, and this is compound 2. Okay, and so here we could still have liters on both, we still have grams on both, and we can still have representative particles on both. Okay, and remember, representative particles can be atoms, formula units, molecules, or ions. Okay, it can be any of those. And so now when we do something, say we have 15 liters, so we'd write 15 liters of N2 gas. Okay, liters of N2 has to go on bottom, so it maybe is 22 point, or it has to be 22.4, and that's always over 1 mole of N2. Okay, now we want to go to hydrogen. Okay, so we started here and we want to end there. So those are the two that are involved in the mole ratio. Okay, so we need to find our mole ratio that involves those two, and it's this first one here. So we're just going to plug that in, canceling out units. So we're going to put 1 mole of N2 on bottom. Okay, so liters cancels, now moles of nitrogen cancel, and we have 3 moles of hydrogen on top. Now we can do 1 mole of hydrogen on bottom, and we can put the 22.4 up here. Of course, these cancel out, and so it's just 15 times 3, which gives us 45 moles cancel out, liters of hydrogen. Okay, and so we're just adding that one more conversion factor, and it's always from where you started to where you finished. Now from this we can do what is called the limiting and the excess reactants or reagents, either one. And what this is talking about is just this idea of one of these two things stopping the reaction. So we can calculate what the perfect thing would be. We can start out with grams and convert them both to moles, or we could start out with liters and convert it to moles. Okay, so we would want to look at the moles. So let's just make up some mole ratios so we don't have to count. So we can do 2.3 moles here, and maybe 16 moles over here. Now, just because this is the biggest number doesn't necessarily mean that it's going to be in excess. Okay, we have to do the calculation. So we would just start out with 2.3 moles of N2. Okay, and then on the bottom you would put 1 mole of N2, and then using that conversion factor, we're going to hydrogen, so you use 3 moles of hydrogen on top. And when you do that, we're going to get 8.1 moles of H2. Now, if we compare that to the 16, in this case, this is the perfect reaction, remember. And so we're going to have plenty. In fact, we can see that hydrogen is going to be in excess here. Okay, so now if this would have said 1.6 moles, then we would have saw we were not going to have nearly enough hydrogen, and it would have been the limiting reactant. So since it says 16, we know that nitrogen is going to be our limiting reactant, and nitrogen is going to run out first. Okay.